All right. This is the last lesson of this unit. No, just kidding. It's the next to last lesson in this unit. Can't forget rational equations and or whatever it's called. So this is the penultimate lesson of this unit. Let's dive in and take a look. I really like this particular unit because being able to convert from radical form to exponential form is super useful. I know it ends up with fractions. You can see fractions, and so that's probably freaking you out a little bit, but it makes a lot of things a lot easier to understand. See the last lesson where I was like, this is hard to understand this way, but this is easy because 4 divided by 2 equals 2, right? That's easy to understand, right? It helps us do reductions, and let's talk about the lesson. Here we go. So radical form is where we have the power, which is y, the power, and then we have the root, right? So the x is the root, right? And this works to convert it to exponential form. This works whether the power is on the inside of the radical or on the outside. Very often when we're doing simplification problems, we will want to convert it to something like this, because if you take the root of a number first, then you get something smaller, and then take the power. And so it's easier going to be to do stuff in your head and do whatever else. It's going to be easier to work with. And so that's often true. So in order to convert radical form into exponential form, you can see that we take and keep the base the same, and we raise it to a fraction power, a rational exponent, right? So the power goes in the numerator, right? See how they match? Easy peasy. And then the root, whatever it is, it's 2 if it's square root, or 3 if it's cube root, etc. Root goes on the denominator. Let's do some examples just converting between the two to show you how easy it is. Okay, so it's easy if we don't have too many things on the board. All right, so we're going to do these 3 examples, and it's just going to take just a second to get it done. It's going to be how easy it is. We're going to write x to the 1/6 in radical form. So on the top is a 1, so the power is 1, so it's x to the first. The root is 6, so 6. So we're going to convert this into 6th root of x. That's easy peasy, right? No big deal. This one, we want to write the 4th root of x in exponential form. So there is just a 1 that's a power. There's a 1 here, and it's raised to the first, so it's going to have a 1 in the numerator like this one over here, but it's going to have a 4 in the denominator, so x to the 1/4. That's no big deal. Now, this one is a little bit harder. Not a lot. It's got 4th root and it's got 7th power. So you could, both of these are correct. You could do this as the 4th root, right? The root is the denominator of y to the 7th. So you could do it like that, or you could do it as y to the 7th, right? Still the power. And we're going to do the 4th root of that. So either one of these answers would work, and I'd accept either one. Would be if this was the original problem. What about this one? This one, we've got a -5 as the root, and -5 as the power and 3 as the root. So we're going to keep the base the same. So it's going to be c as the base, and the power is -5, so -5/3. Now, it really just says convert this to exponential form. So in this particular problem, we could just circle it and move on. But if it said something like simplify or whatever, then we would want that negative power to go away. So this would turn into 1/c to the 5/3. So arguably, on this particular problem with these particular instructions, this will be fine. And in a lot of other cases, that you would want to get that negative exponent out of there, because we don't usually like that in our answer. So let's do another thing. So we're going to evaluate each expression, and we're going to do this without a calculator. Basically, it's going to be easier than you might think. So this 81 to the negative 1/4. What we're going to do first is we're going to deal with the negative exponent. We just kind of remembered or were reminded what that does. The negative exponent makes it change level, so it moves from the top to the bottom. So negative 81 to the 1/4, right? So now it might be useful to convert this into radical form. That way we can kind of see what's going on. We're used to seeing things with numbers in them like that in radical form. So let's do that next. Okay, so this in radical form, it's got a 1 as the power and a 4 as the root. So it would be 1 over the 4th root of 81. Now, this kind of goes back to what we've been doing before, right? So if we can convert this 81 into something to the 4th, right, then the 4th and 4th roots would cancel. So is something to the 4th 81. So that's where we just kind of pull out our calculator and start trying stuff. Wait and see what happens. So what do we want to try? Well, 2 to the 4th probably not going to work, right? Let's see what happens. 2 to the 4th, 16, not big enough. What about 3 to the 4th? You're like, that's not going to be big enough. Oh, but it is. 3 to the 4th is 81. Right? That's great. So we can turn this into 1 over the 4th root of 3 to the 4th. Now the 4th and 4th root cancel, leaving us with an answer to this one of 1/3. Right? Make sure you're showing all your work on these particular problems when it's just a number, because I understand that you can just punch it in your calculator, and that is a skill that's worth having. But as we've seen in this lesson and we'll see in the future, it's not always going to be numbers. So knowing how to manipulate this and knowing how to do all of this by hand is a good practice. And they won't always come out clean like this, right? You know, we kind of did that in the last lesson too. So make sure you're showing this work and seeing what's going on. So we're going to do this the same way. We're going to convert this into radical form to do it. Okay, so we're going to convert this to, I don't want the same color. That'll get confusing possibly. So we're going to convert this into the cube root of 216 squared. So this one, we've got the cube root of 216. So does the cube root of 216 exist? Yes, it probably does. Is something cubed 216? We can double check and see. How about 4 cubed? Is that 216? No, it's 64. What about 6 cubed? It's not going to be 5. There's no way that works, right? 6 cubed is 216, right? So we can turn this into, that you might could put in the calculator and get away with it, right? The cube root of, what do we say? 6, right? 6 cubed. Nope, that's a squared. Squared. Oh, 6 cubed. Cube and cube root cancel, right? Sorry, I got distracted. There was yelling upstairs, and I was distracted. 6 squared, and 6 squared, we know, is 36. Great. Let's do another one. The formula, C equals C naught times 1 plus R to the n, can be used to estimate the future cost of an item due to inflation. C represents the future cost, C naught represents the current cost, R represents the rate of inflation, and N represents the number of years for the projection. Suppose a video game system costs $390 now, so that'd be the initial cost. So that means that C naught is $390, right? How much would the price increase in 6 months? So N equals 6 months. I'm going to write that with units, months, because it says in our formula that N is the number of years. So how much is 6 months in a year is, if we convert that to years, well, that would be half a year, right? Half a year. Annual inflation rate, so R equals 5.3. Now, percent. Now, in order to use a percent and do the math with the percent, we need to convert this percent to a decimal. To do that, of course, we just move the decimal place over once and twice, right? So R equals 0.053. So now we've got the thing. We're going to use this formula that we were given in the problem. C equals C naught times 1 plus R to the n. And then we just plug stuff in where it goes, right? So C stays C. C naught is 390. 1 plus 0.0453 would be 1.053. Kind of cheating and doing those two steps in one, right? And n was 1/2. Okay, so now it's just an order of operations problem, and pretty much, since we got weird decimals and things, pretty much a calculator problem. So this to the 1/2, which would be the square root of that, right? That's why this problem exists in this lesson. So we can put in the square root of 1.053, enter. You could also put 1.053 to the 1/2 in most calculators. But we have that, and I'm going to leave that in my calculator, right? Because now, and this will work with your scientific calculators and all the things, because now I can just push times. Remember, it pulls up the little answer, which is whatever we got last time, times 390, enter. So that console is going to be $420 thereabout. Probably should add is approximately equal to 420, right? So, is that right? Was it 420 or 410? Where did I get 420? Oh, I know what I did. $400.20. $420, right? So is that what it's asking for? Let's double check. Go back to our problem, make sure we're answering the question that's asked, right? Suppose a video game costs that. How much would the price increase? So the price would increase by this minus 390, right? The original price, which is about $10, right? So it's going to increase by about $10, assuming this formula holds steady for in times less than a year, which I know, admittedly, in this situation, there are other variables involved and, all that and stuff too. But there you go. There's some practice with that. So let's do another problem. So this one is way easier than you might think. Let's take a look at it. So we have a to the 2/7 times a to the 4/7. Well, we have like bases multiplied. When you have like bases multiplied, what do we do with those exponents? Well, you add them, right? So these have like denominators. So 2/7 plus 4/7 is 6/7. So this turns into 8. No, that's an A. A to the 6/7. Bam. All right, now this one is a little bit trickier, kind of. It's deceptively trickier. It's not that bad. I'll show you. So we have here, and this example is a good tie back to last lesson. This is kind of it's going to lead to where we're trying to rationalize the denominator of something that's not a square root, because this is going to be a 6th root in the denominator. Let me show you. So this is going to turn into it's going to turn into 1 over b to the 5/6. Now, this is one more step in like what we saw earlier, where I was like, well, and it would probably, if it said simplify, which it does, you would have to get rid of that negative exponent. Well, we also don't like radicals in the denominator, and we've now learned that fraction exponents are radicals, so we've got to get rid of this 6th root of something, right? We can't have a 6th root of something down in the denominator. So last lesson, we learned that you just multiply the top and bottom by the square root. Well, this isn't a square root, it is a 6th root. What we need to do, and this particular example kind of ties in and leads us to this example. What we need to do is we need to multiply times whatever would turn this into a 1. And so we're going to multiply times b to the 1/6 over b to the 1/6, right? Because 5/6 plus 1/6 is 1, right? And so that's why this works. Now, so if we had like over a to the 2/5, right? So we would multiply, in this case, a to the 3/5. So that's why it didn't work out in the last lesson where it was something to the fourth, I think. I think it was 1/4. And so to get rid of that one in that particular example that we decided to wait and push off to this lesson, you have to multiply times a to the 3/4, which would be, as we know now in this lesson, you'd have to see that you had to multiply times the 4th root of a cubed, right? And so it's much more confusing than just looking at, okay, what do we add to make it a 1? Just simple common denominator stuff. This is so much easier than trying to wrap your brain around it with radicals in there, right? So 1 times b to the 1/6 is b to the 1/6. Now, we just kind of learned that in the denominator, this is going to end up being b to the 1st, right? Because 5/6 plus 1/6 is 1. So this is b to the 1st. So we could circle this. If the instructions said write your answer in radical form, then we would just convert this to the 6th root of b over b. Right? So either one of those would be the correct answer, or if it told you what form to write your answer in, you'd have to do it in that particular form. Easy peasy. We've already done a bunch of examples. It's only 16 and a half minutes in. We're doing great. Let's do some more things. Right. So we're going to combine even more things into one, and we're going to make this work. So this, some of the earlier problems, it was helpful to solve the problem to convert it into radical form. Well, in this one, that may be true, and it may be no. Let's start by looking at this and seeing, okay, so we've got a 27 on the top as the base, or the radicand in this case, but we've got a 3 on the base. But if we have like bases, we can do all kinds of stuff. So can we turn 27 into something cubed? Well, the likeliest suspect, just kind of thinking about the number sense that we have, is 3. So let's check it. So is 3 cubed 27? Yes, it is. So let's do that. Let's turn this into 3 cubed. And then we're going to leave the 4th root on here. We're going to do something with it in a second. 4th root, and then over the square root of 3. So we've got like bases and whatever else. Well, when we have like bases divided, you subtract the exponents, right? So we need to turn this into something that we can subtract. So we need to turn this now into rational form. So let's do that. Let's turn this into 3 to the 3/4, right? The root goes in the denominator of that fraction, and the power goes in the numerator, over 3 to the 1/2. Remember, for radicals, if it's nothing there, it's a 2, right? So now we just need to do 3/4 minus 1/2. 3/4 minus 1/2 is 1/4. So this turns into 3 to the 1/4. So we could circle that and move on. Or if we wanted to, we could convert it back to, and really in this case, if we wanted to, is usually in math, we want to leave things the way we found them. And by that, I mean, if we started with fractions, end with fractions. Don't start with fractions and end with decimals. Don't start with decimals and end with fractions. In this case, don't start unless it tells you in the instructions. Don't start with radical form and leave it in exponential form. So we're going to do one more thing and turn this into the 4th root of 3. I might count but either one right, because it doesn't say what form. It's just usually best practice to leave things the way we found them. So let's take a look at this particular example. So this particular example with the 64, again, we're going to kind of do something similar, right? If we can turn this into 64 equals something cubed, then that would be great. It's not 2 because that's 2 cubed is 8, and it's not 3. We just did that. So what about 4? I think we did that kind of on accident earlier. I think that works, right? 4 to the third equals 64, right? So that's great. So we can turn this into and what I want to do actually is convert this, because this is going to save us some time. I want to go ahead and convert this into exponential form. My nose is all snarfy, sorry. So 4 cubed z to the 6th to the 1/3. Now, you notice we have power to a power. This also kind of distributes. It gets applied to everything. What's 1/3 times 3? 1. All right, so this turns into 4 to the 1st. And then what's 6 times a third? 2. Z squared. That's so much nicer, right? Than having to turn this into z squared cubed and then do all that and cancel the thing. It's just a third times 6 is 2. That's like that's easy. You don't even have to write an intermediate step. You just do it. No big deal. Let's do one more. Oh, it's so scary. It's a little scary. It's not that bad. So simplify. What do? Well, we don't like radicals in the denominator. This is a radical. This is the denominator. So we don't like him. So how do we get rid of radicals in the denominator? Well, what did we do last lesson? We multiply times the conjugate. So it's the same difference. So what is the conjugate? The conjugate is the denominator with the sign changed in the middle. So that's exactly what we're going to do here. So we're going to multiply this times 3x to the 1/2 minus 2 over 3x to the 1/2 minus 2. And then we're just going to distribute. Now, we already walked through in the last one, and so I'm going to just remind you in this one that when we do the conjugate in the denominator, that outside and inside are going to cancel. So all we have to do is the first and the last in the denominator. Now, the numerator, on the other hand, we need to do all of the things, right? So on the denominator part, we're going to just do this times this and this times this. Easy peasy, lemon squeezy. Wait, no, that's not right. That's not right at all. The first and the last. The outside inside cancel. What I had done was the one that was going to, yeah, just the first and the last is all you have to do. Now on the top, I'm going to go ahead and change colors again just because we're going to have a lot of lines happening. We got to do this times this times that, and this one times this one, and this one times that one, right? We've got to do all of those things. So in the numerator, we've got x to the 1/2 times 3x to the 1/2, 1/2, x to the 1/2 times x to the 1/2, like bases multiplied, add the exponents. 1/2 times 1/2 is, 1/2 plus 1/2 is 1. So this turns into 3x to the first. If it's to the first, we leave it off, right? X to the 1/2 times -2 is just -2x to the 1/2, right? All right, now then we've got -2 times 3x to the 1/2, so that's -6, because -2 times 3 is 6, or -6, x to the 1/2. There's nothing to combine with, he stays there. And then -2 times -2 would be +4, right? Then in the denominator, the outside and inside are going to cancel, so we're just going to do the first and last. So the first is 3x to x to the 1/2 times 3x to the 1/2. So we've got x to the 1/2 times x to the 1/2. I'm going to write, I've said that out loud a couple times, but just because of my visual folks, my highly visual folks, right? This is what we're doing. We've got like bases multiplied. We add them. 1/2 plus 1/2 is 1, right? So this turns into 9, because 3 times 3 is 9, x to the first. Okay? And then last is 2 times -2, so that would be -4. So see, now there's no more fractional exponents or radicals in the denominator. We just got a little bit of cleanup to do up here in the top. We've got some like terms up here. All right, so we've got 3x minus 8, -2 plus -6, x to the 1/2 plus 4 over 9x minus 4. Now we could convert this to the square root of x, but we're going to leave things the way we found it and leave it in an exponential form here, and there's not really anything we can do. Now you might be tempted, I will throw out just to hit a common mistake, that you might be tempted to like reduce that or something, but we can't get to that because it's attached with addition or subtraction, right? If it was multiplication and division, then we could do some reducing that way, but we can't because addition and subtraction. So this is, in fact, as simple as this one gets. So, believe it or not, with however many examples that was, we're done. And that's it for this particular lesson. We'll see you in the next one, which will be the last one for this unit. It's a good one. We get to use all these tools we've been gaining to actually do something cool with it and all those things. So it's a good lesson. It's a good unit. I like it. Hope you're having fun. I'm having fun. We'll see you in class if you're one of my students. Otherwise, see you on the internet. Goodbye.